Precalculus, lesson P.4 over polynomials. In this lesson, we're going to be talking about the definition of a polynomial, their different components, and also operations with polynomials, in this case, addition, subtraction, and multiplication. First off, though, what is a polynomial? A polynomial has many terms and have to have whole number experts. Terms, just as a reminder, are those parts of an expression or a polynomial that are separated by addition and subtraction signs. So as you can see here, I've gone ahead and divided those into the different terms. The degree of a polynomial is the highest or largest exponent of the polynomial. In this case, it would be n. Leading coefficient is the number in front of the variable with the biggest exponent, and the constant term is the term or the number without a variable in this case, so the a naught. When we're talking about polynomials in standard form, this means that it has been written such that the terms are written in the order of descending powers, or from highest to lowest. Some special names for polynomials that we are given are based on the number of terms. So if a polynomial only has one term, it is called a monomial. If it has two terms, it is a binomial. And if it has three terms, it is a trinomial. Simplified polynomials with four or more terms have no special names and are just referred to as polynomials. So in these next couple of examples, what we're going to do here is we're going to talk about if this is a polynomial or not. And if it is not, we're going to give a reason why. In this first case here, notice that we have 2x plus 3x squared minus 5. In this case, this is a polynomial, since all exponents are integers and we have whole number coefficients. Notice in this case, the degree of the polynomial would be 2, since that is the highest exponent. The number of terms here is going to be 3, since in this case, making this a trinomial. The leading coefficient is also 3, since that is the coefficient on the x squared term, and our constant term here is going to be negative 5, since it is the term with no variables. If you look at the second one here, notice we have on the second term there an x to the negative 1. Polynomials cannot have negative exponents. Remember, it must be a whole number exponent. I might have missaid that earlier. In this case, exponents must be a whole number. In that case, 0 or greater. There's another type of exponent that it cannot have is fraction exponents, since fractions are not whole numbers. If we look at number 3, in this case, if we were actually to go ahead and do our distribution here, we would get 2x squared plus 2x plus 4x plus 4. And if we combine those like terms, we get 2x squared plus 6x plus 4. And notice this would be a polynomial written in standard form. In this case, giving us, yes, that it is a polynomial. Our degree here would be 2, since this is the highest exponent. The number of terms would be 3, making this a trinomial. In this case, our leading coefficient would be 2, since it is the coefficient for the x squared term, and our constant term here would be 4. Now, you could probably also tell that this is a polynomial without having to do that distribution. In this case, we notice that we have no negative exponents and no fraction exponents, so this would also be, that would be another way for us to tell that this is a polynomial. In our last example here, we have 2x plus 3 over x. This is not a polynomial. The reason why here is because of the x in the denominator. Since we cannot divide that x evenly into every term in the numerator, that means that this is its simplified form, leaving that x in the denominator. And a polynomial cannot have any variables in a denominator. So in this case, to not be a polynomial, in this case, that means that we cannot have negative exponents, fraction exponents, or exponents in our denominator when simplified. When we're working with adding or subtracting polynomials, we always want to make sure that we're paying attention to the actual sign that is between the two polynomials given to us, in this case subtraction. So what I like to do first is go ahead and distribute that negative sign to every term in the second polynomial, since we can treat it as like distributing a -1. So I'm going to bring down everything in that first polynomial, and then go ahead and change the signs in the second, making this a -16x cubed plus 3x squared minus 3x minus 15. From here, then, what we want to do is combine like terms. So for, in this case, the -17x cubed and -16x cubed become -33x cubed. And I'm going to cross those off, make sure I've already taken care of them. If we go to our x squared terms, we have a 4x squared and a 3x squared, which are going to combine to 7x squared. The x terms here are the 11x and the -3x, which combine to -14x. Then our constant terms of -5 plus 15 are giving us a +10, leaving us here with the final polynomial answer of -33x cubed plus 7x squared minus 14x plus 10. Notice here the degree would be 3. This would be a 4-term polynomial. The leading coefficient would be -33 and the constant term 10. When multiplying polynomials, we can really think of this as distributing every term in the first polynomial to every term in the second polynomial. So it's kind of just like multiple distribution. So for example, we're going to take that 5x times everything in that second polynomial, giving us 15x squared, or sorry, x cubed, minus 25x squared plus 20x. And then we're going to distribute that -2 to every term in the second polynomial, giving us a -6x squared plus 10x minus 8. And from here, then, we can just combine like terms like we did before. So we're just going to bring down the 15x cubed, since there's no other cubed term, combine our x squareds, so we get -25x squared plus a -6x squared, giving us a -31x squared. Combine the x terms, the 20x and the 10x, to give us 30x, and then bring down that -8 since it is the only constant term, giving us the final answer of 15x cubed minus 31x squared plus 30x minus 8. Now, in the case of where we're just trying to find the product of two binomials, in this case, we can use the FOIL method. This is a quick and easy way for us to be able to multiply them. And the FOIL here stands for the product of the first two terms. The O is for the product of the outside terms. The I is the product of the inside terms. And the L is for the product of the last. So to illustrate this, let's say we're trying to multiply 7x minus 5 times 4x minus 3. We're going to start by taking the first terms, or the 7x times 4x, which will give us, in this case, a 28x squared. We're then going to multiply the outside terms, the 7x times the -3, which will give us, in this case, a -21x. We'll multiply the insides next, the -5 times 4x, which will give us a -20x. And finally, we can multiply the last two terms, the -5 times the -3, which will give us a +15. From here, then, all we need to do is combine our middle two terms, and so our final answer will be 28x squared minus 41x plus 15. Now, when we're multiplying binomials, what you're going to see here is there's certain special products or patterns that will emerge as the more that you do. There are several products that occur so frequently that it's convenient to memorize the form or pattern of these formulas. So, assuming that A and B represent real numbers, in this case, the big ones that we want you to know by heart is, first of all, the sum and difference of two terms. So if we have A and B being the same, where it's A plus B and A minus B, well, then this will always multiply to the square of the first term minus the square of the second. Okay, so that gives us A squared minus B squared. Similarly, if we're squaring a binomial, where in this case, if it is a plus b squared, remember that would be the same thing as a plus b times a plus b. This is always going to be equal to the square of the first term plus 2 times the product of the two terms plus the square of the second term. Similarly, for the difference, if we have a minus b, it will be a squared minus 2 times ab plus b squared. Notice it's the exact same pattern, but the second term always takes on the sign of whatever the original binomial was, either a plus b or a minus b. If you don't feel like memorizing these, it is totally fine for you to always just remember to FOIL if necessary. Now let's consider polynomials in several variables. And what we mean by that is, in this case, x and y. Polynomial in two variables contains the sum of one or more monomials in the form a x to the n power y to the m power. Here, a is the coefficient. The exponents n and m represent whole numbers, and then the degree of that monomial is found by adding those exponents together. The degree of the polynomial in two variables is the highest degree of all its terms. So the term that has the highest number of variables, or the highest sum of exponents, is the degree of the overall polynomial. So like in this case, if we were to try to multiply these binomials in two variables, 7x minus 6y times 3x minus y, notice there, since they're both binomials, we can use the FOIL method. So we're going to start by taking the 7x times the 3x, the first two terms. And if we do so, we're going to get 21x squared. Then we do our outside terms, 7x times a negative y, which will give us a negative 7xy, written as one whole monomial. We'll do our insides next, giving us a negative 6y times 3x, giving us a negative 18xy. And finally, we'll do our last, negative 6y times a negative y, which will give us a positive 6y squared. And then we're going to write this in our standard form using alphabetical order. And so we'll get 21x squared minus 25xy plus 6y squared. Notice in this case that the degree of the overall polynomial is going to be 2. Since if we look at each of these terms, the 21x squared has two variables, the two x's. The second term is also degree 2 since it has one x and one y. And the last term is also degree 2, which because it has two y's, the y squared. So the highest degree out of all the terms is 2, making the overall degree of the polynomial also 2. Please feel free to rewind and look at any of these examples if you need to go back.